Right, very good afternoon. Today, let's discuss the time series data analysis. So far, we have discussed cross-sectional data analysis and then how to run the regression model for the cross-sectional data, and then how to test the model efficiency by using heteroscedasticity, autocorrelation, normality, and the multicollinearity. Right, those or the model stability by using the Kusum test. Today we discuss the time series data analysis. This is because most of the time series, most of the economics and the finance data are time series. So then this lesson discuss the basic time series model, autoregressive and the moving average models. Also the how to stationary and non-stationary time series. Those two topics are discussed today. Right. So then time series, you know that your data series are changing with the time. So then we call these data are time series. Time series is a sequence of numerical data in which each item is associated with a particular instant in time. So then one can quote numerous examples. So then most of the data are the monthly and the unemployment, monthly unemployment and weekly measures of money supply, daily closing prices of stock indexes, exchange rate, daily exchange rate. Right, so then these data are the time series. So then current progress in computer technology, we have daily series of interest rate and then stock prices and the exchange rate daily. We have daily data, monthly data, or the quarterly data and annual data. Right, those data we call is the time series data. So then an analysis of single sequence of data, we call it univariate time series analysis. An analysis of several set of data for the same sequence of time period is called multivariate time series analysis, or more simply multiple time series. Right, when we before that moving to the time series data analysis, so then I would like to explain brief introduction about that why we are using time series data analysis. So then in the past there has been very little communication between econometricians and time series analysis. Econometricians have emphasized economic theory and the study of dynamic relationships. Lag variables were introduced, but not in a systematic way, and no serious attempts were made to study the temporal structure of the data. Right, so then in econometrics and time series analysis, we use the lag variables, we included to the lag variables to the model, but not in the systematic way. The theories were imposed on the data even when the temporal structure of the data was not in a conformity with the theories. Time series analysts, on the other hand, did not believe in economic theories and thought that they were better off allowing the data to determine the model. The time series data analyst So then theory as it is, and they do not believe. Then since mid-1970s, these two approaches, the time series approach and the econometric approach, have been converging. Then econometricians now use some of the basic elements of time series analysis in checking the specification of their econometric models, and some economic theories have influenced the direction of time series work. Right, in the time series data are non-stationary, and we need to check that with the time our data are stationary or not. The stationarity and non-stationarity of time series. Right, this is the stationary and non-stationary data. Right, this is the theoretical explanation of the stationary and non-stationary. Here, mean of the time is expected our independent variable, and the variance of the time and the variance of that our variable is a autocovariance. Right, so then to test that stationarity, right, I'm not that explaining more about the theory. Let's discuss what is stationary and what is non-stationary by using the practical example. Right, so then this slide explain the theoretical background about what is stationary and what is non-stationary. Unit roots in time series models. The shocks in usually used to describe an unexpected change in a variable or in the value of the error term at a particular time period. Right, that some in time series data, when whatever the variable changing with the time, so that the data series are not smoothly going on. There are some shocks came. Those are the unexpected changes came. So then our data series change. When we have the stationary system, effect of the shock will die out gradually. When we have the non-stationary system, effect of shock is permanent, right? So then it doesn't go. But when we the stationary system, the effect of the unexpected change will die out gradually. When we use the data as it is, it includes those unexpected changes. These unexpected changes, effect of these unexpected changes is permanent. So then analysis is based on these unexpected changes. There are two types of non-stationary. One is unit root. It is homogeneous non-stationarity. Other one is explosive non-stationarity. That is a shocks to the system. So the economic system or the financial market assume that shock. The reason, for example, is a political influence or the election, right? It is a shock to the share market, but that shock become more influential as the time goes on, but can never be seen in real life. Right, this is the theoretical background of the unit root testing. right? So this if there is a one unit root or the near one of the autoregressive polynomial, so then we use the difference. We use the difference in variables. That means we consider the first difference of the series. If the unit root near of the moving average polynomial, so then we use over differentiate. So then unit root test whether our data are stationary or not. We can check the stationarity by using the Dickey-Fuller test. Right, this is the Dickey-Fuller test is the simplest approach to test the unit root. Begin with autoregressive one model. So then here yt is the dependent variable, and then yt minus 1, it is the lag value of the dependent variable. The Dickey-Fuller test doesn't consider that that is autonomous, this exogenous variable in the model theta 0, but actual model with theta 0 and not theta 0 gives different results. In the actual model there is this theta 0, but it is not this model, so then yt equal yt minus 1. Right, this is the hypothesis of the Dickey-Fuller test. So then this is the, to simplify the computation, we subtract the yt minus 1, that means lag value of the dependent variable. We subtract from this from both sides. Then delta yt minus yt minus yt minus 1, it is delta yt, it is theta 0 plus sigma yt minus 1 plus at. If you know that this theta equals 0, then system has a unit root. Then delta yt equal theta yt minus 1. That means past value, that is the one characteristics of the time series data, when the past value impact to the present value. So then we need to, by this test, we Dickey-Fuller test, we test whether our series has a unit root. If it is 0, so then this total part is 0. Then the delta yt equal at. Whether you know that this value is less than 0. Right, the Dickey-Fuller test, it was introduced by the Dickey and Fuller in 1979. So then it is pure random walk. This process is pure random walk. This process is random walk with drift, right? With drift. This is a drift and a linear time series. There are 3 types. Right, that means when the time series is flat and the potentially slow turning around 0, then we use the first one. When the number of argument in legs is determined by minimizing the Schwarz-Bayesian information criteria and Akaike information criteria. Right, so then here we can we hypothesize that the data model to be difference to make it stationary. the data is stationary and doesn't need to be difference. Right? Null hypothesis mentioned that data is stationary and no need to be difference. This is data need to be difference to make it stationary. Right? This is one. Right? This is the theoretical explanation of the Dickey-Fuller test. Right? So then, if the critical value of the Dickey-Fuller is minus critical value minus 7.3, alpha is 0.05, we reject our HO, then that means there is exists a unit root. Then we need to take difference to be able to estimate the model for the series. Right, this is the theoretical rationale behind the augmented Dickey-Fuller test. This is the practical issue for the implementing of the augmented Dickey-Fuller test is the specification of the lag length. How many lags we need to include. If the lag length is too small, then the remaining serial correlation in the errors will bias. If the lag length is too large, then the power of the test will suffer. Right, we need to select the optimal, what is the how many lags we need to include. Right, here we include, in this example, we include 2 lags. Right, in this case, examine the original model. Our original model is yt equal theta 0 plus lag value of the dependent variable and the first lag value of the first difference of the lag value of the dependent variable and the second difference of the lag value of the dependent variable and the AT constant. So then OLS estimation, this is the OLS estimation. Right, we calculate the augmented Dickey-Fuller test, but no need to calculate manually. Right, then just to understand. So then it is our null hypothesis is a data model to be differenced to make it stationary. Data model is stationary, no need to be difference. So then we reject the data need to be difference. If the test statistic is positive, you can automatically decide to not reject the null hypothesis of unit root. Right? If the test statistic is positive, you can automatically decide not to reject the null hypothesis. Augmented model can be extended to allow moving average terms in AT. Right, the Dickey-Fuller developed this model, this test in 1984. So then, not only that, based on the shortcoming of the augmented Dickey-Fuller test, Philip Pearson have developed a more comprehensive theory of unit root non-stationarity. The tests are similar to the augmented Dickey-Fuller test. The Philip parent test differ from the augmented Dickey-Fuller test mainly how they deal with the serial correlation and the heteroscedasticity in the errors. In particular, where the augmented Dickey-Fuller test use a parametric autoregression to approximate the AMA, autoregressive moving average, ARMA, autoregressive moving average structure of the errors in the test regression. The Phillips and Perron test ignore any serial correlation in the test regression. This Phillips-Perron test, PP test, gives same conclusions as the augmented Dickey-Fuller test says. The calculation of the test statistic is little bit complex. Right, this is the PP test, but this is the theoretical one. This is the hypothesis, the same as the augmented Dickey-Fuller test. Right, this is the advantage of using the PP test. Is the PP tests are robust to general forms of heteroscedasticity in the error term. Another advantage is the user doesn't have to specify the lag length for the test regression. So then we no need to give the PP test. They select how many lags need to be improved. Then PP tests tend to be more powerful, but subject to more severe size distortions, size problem. Then actual size is larger than the normal when autocorrelation of the errors are negative. More sensitive to the model specification. Plotting the ACF autocorrelation function helps us to detect the potential size problem. So then economic time series sometimes have negative autocorrelations, especially at lag 1. We can use Monte Carlo analysis to stimulate the appropriate critical values. Right, that may not attract you to do. However, there are many criticisms for these two tests. Right, those are some criticisms. Right, one is that power and size. Right, based on that shortcoming of the Dickey-Fuller and the PP test, there are a variety of alternative procedures have been proposed to solve these problems, particularly that power problem. But augmented Dickey-Fuller test and the Phillips-Perron test continue to be the mostly widely used unit root test. Right, in the future that may be changing. Currently, these two tests are the mostly widely used tests to test the stationarity. The stationary time series may look like non-stationary when there are structural breaks in the intercept or trend. When the unit root test leads to false non-rejection of the null when we do not consider the structural breaks. The single breakpoint is introduced in Pearson in the regression model. Perron extended it to the case of unknown breakpoint. If you wish to read more about the PP test, you can see the Perron, this article, to know more about the structural breaks. right? So then it's in this power of the ADS, rejection of the frequencies of augmented Dickey-Fuller test. Augmented Dickey-Fuller tests are biased towards non-rejection of the null, and the rejection frequency is universally related to the magnitude of the shift. Right, this is then what we have discussed so far. When the time series data are stationary, we need to check that time series data when something happen, when unexpected changes, shocks happen, the data series do not smoothly going on. So then we need to identify whether our data series are stationary or not. To check the stationary or not in econometrics, uh, there are two types of test. One is augmented Dickey-Fuller test, and the one is PP test. Right, so then that's what you need to understand. First one is whether time, if you are using for your research or for that analysis your research data, first one you need to uh, consider that whether your data are stationary or not. If it is stationary, right, how to check whether the series are stationary or not? By using the Dickey-Fuller test, augmented Dickey-Fuller test, and the PP test. Right, now you know that, go to the LMS. Now go to the LMS and then download, you know, that this unit root test in model 1 or 2. Here I download that model 2, Dickey-Fuller test in model 2. Right here, this is augmented Dickey-Fuller test, unit root testing. Unit root testing to tackle the autocorrelation problem. Dickey-Fuller, DF means Dickey-Fuller. Dickey-Fuller has developed Dickey-Fuller has developed a test called augmented Dickey-Fuller test. Right. When augmented equipolar test, the hypothesis is hypothesis is uh, the data need to be to make it stationary. Then the alternative hypothesis is the data is stationary and doesn't need to be difference. Right, now go to the quick. Go to the quick. Right, download the data set. Download the data set. Go to the quick. Right, the quick. You can see the group statistics. Right, go to the quick and then group statistics. Under the group statistics, uh, here there is a series, not a series statistics. Right, quick, series statistics, unit root test. This one, right? You remember the path, right? The time series data, it has an autocorrelation issue, right? If the data series has autocorrelation issue, then we need to check whether our series has a autocorrelation, a series has a unit root or not. Whether series are smoothly running or are there any drift of the series. Right, then you know that select the Dickey Fuller and the Philip Perron test is used to test the unit root. And then click you know that now unit root test. You need to give the number of series name, but in this case it is Y. Our series is Y. Click OK. Right, so then in this unit root test box, so then there are three options: test for the unit roots, levels, first difference and the second difference. Right, first what we need to do is lag length. Lag length, in the lag length box, we automatic selection, select the automatic selection. Right, include the test equation. There is a text equation here, intercept, trend and intercept and non. All test statistics value should greater than augmented Dickey Fuller value. If the absolute test statistics is more than critical value, it doesn't have that is a data. This Right, go to the quick group statistics and no, series statistics unit 2 test. Our variable is y. Right, so then maximum leg length, right, this is if uh, the probability value is less than, if the probability value it is less than uh, if the probability value is less than the critical value, so then we accept our alternative hypothesis. What is our alternative hypothesis? We have a null hypothesis. Data need to be differentiated to make it stationary. Alternative hypothesis. Data stationary and no need to difference. Right, if the hypothesis value if the probability value is less than 5%, we accept our alternative hypothesis. Right, so then here probability value is 0.069. It is less than 0.05, means 5%. Right? Not less than, it is greater than. Then we reject the alternative hypothesis. It implies that data differentiated to make it stationary. Right. Then what you need to do is go to the again quick series statistics unit 2 test and variable is y, and then go to the first difference. Go to the first difference. Go to the first difference, and then it is intercept. Trend indicate the test equation. There are three types of equation, whether it has an intercept, it has a trend and intercept, and it has a none. So then we need to do is everything test by step. Now click OK. So then select automatic selection. Maximum lag length is 3, and then now click OK. Right, now you can see that here probability value is 0.000. Probability value is less than 5%. we accept the alternative hypothesis. It means no need to second difference, right? No need to do the second difference. Right, in the first difference, series of the first difference are not stationary, are stationary. Also then if you go to the before test in the unit root, you need to see the series of the graph. It is y. Graph type is basic type graph and the line and symbol. Now this is the graph. Now you can see no smooth pattern. You can see up and downs. I drift here, so then we need to remove this. Now generate our series. That's why it is not smoothly going on. Now you know that generate a series, generate plus difference. Y equal d y. Right, then our dy is the first difference. Right, so then draw the graph. It is dy. Name the variables, then click OK. And then graph type is basic, and then line symbol. It is click OK. Right, now you know that it removes some drift in the first difference. Right, first you need to plot the time series data, and at this graph you would expect the time series to be stationary. Also you know that look at the autocorrelation and partial autocorrelation of this time series. Right, so then here check view parallelogram. It is y levels first, then click OK. This is the autocorrelation and the partial autocorrelation. Right, so there is a probability value shows that it is not less than 5%. Right, it means that you can see some drift. Right, it need to be difference. So there is the autocorrelation and the partial autocorrelation and the partial autocorrelation, and this is the probability value. If the probability, check the probability value. Right, so then if the probability value check, that is the last column is a probability value column. In the probability value is greater than 5%. That means we reject our null hypothesis. What is our null hypothesis? Data should be first difference to make the stationary. Right, so then again go to the quick group statistics and parallelogram. Then that our difference variable, that series, go to the first difference of the series. Then click OK. The first difference also that test there is a autocorrelation in this issue, in this series. Also that go to the quick parallelogram. Variable is y, and second difference, it is also that less than 5%. The second difference is okay. Right, now what you need to do is there is a data file capital adequacy ratio. Right, those are the time series data. Right here, this is the capital adequacy. Right, capital adequacy ratio. That is can't remember the name of the variable. So those are the GDP. I means interest rate. Firm is firm. Is capital adequacy. This is unemployment. Assume that for the capital adequacy ratio, what are the microeconomic factors for the capital structure, and then what are the macroeconomic factors that affect the capital structure. Assume that you want to do such type of research. So then what you need to do is you need to collect the data first. Right, so then what you need to do, each series, check unemployment and GDP and interest rate, check whether these series are stationary or not first by using, before that, plot the data. Right, what is the step is? Go to the quick. Right, go to the quick and then graph. Then you need to assume that is you want all the graph adequacy AD. Assets, capital adequacy ratio, unemployment, and give all the series first, and then click OK. graph, go to the graph, go to the one by one. Okay, so then unemployment, interest rate, GDP, CR, CA, right. So then when select all the variables and then use the graph type is a basic graph. If it is basic graph, select under the specific graph type. There are that all the graph types, line and symbols, bar graph, uh, and all the graph types are there. In this time series, we use the line and symbol. Right, then click is a raw data observation in the single graph or the multiple graph. If you want graph for each variable, separate graph for each variables, select multiple graph. Right, then this is the type of graph. So then you can see some graph that has trends. Right, some have that upward trends, downward trends. So then some damps, big fluctuations. Right, this is the data pattern. Right, so then use the data set. Do the following task. Right, first plot the data. Looking at this graph, this time series to be stationary. Right, also look at the autocorrelation and partial autocorrelation time series. Right, then what do you think order process life? Right, do this activity first. Plot the data, looking at the graph, and so then first when seeing the graph, you can check whether series are stationary or not. Then you look at the autocorrelation and partial autocorrelation function to see whether the data series has an autocorrelation. So then what do you think? Which order this process has? It is order 1 or order 2. That means first difference or second difference. Right, so then what you need to do is here what you need to do is first go to the first go to the what I told you to do, that go to the quick and the graph, right? You can use a graph here. Our first variable, put the name of the variable. It is name of the variable is assume that you want to get the unemployment, right? So then click OK. Then there is a graph type. It is line and symbol. Then click OK. Then this is the graph as the data as it is. Then what you need to do is right, then need to draw the graph for the each variable separately. So then what are the variables you want to give, right? What are the variables you need to give? Right here, go to the quick, right, go to the quick graph, right graph, then mention all the graph, right, put all the graph together, right? So then go to the quick again, a graph. So then there are, you know, that many variables in the left hand side. There are many variables, capital adequacy ratio and the constant term, and those are the micro and macro factors that affect the capital structure. Right, first if you want to, you know, that see the macroeconomic variables, here interest rate I, unemployment UN, and then GDP, right, those are the variables. So then click OK. Then it is the graph type, select the graph type, those are the basic line graph, and select the type of the specific graph is line and symbol, and then not only the single one set of graph, so then you need a separate graph for each, then select multiple graph and click OK. So then this is these are the graph. Then you can see the whether the series are stationary or not. Right. So then after that, check whether the partial correlation, right after that, check the partial correlation, autocorrelation and the partial autocorrelation of the time series data. Right, go to the quick series statistics and the correlogram. You need to give that one by one for each variable. First that give the variable unemployment. First levels. First check the levels. Right, in the first check the levels, you can see the last column, probability. The probability of the partial autocorrelation and partial autocorrelation, it is less than 5%. That means there is a autocorrelation problem. What is our null hypothesis? Our null hypothesis is no autocorrelation, and the alternative hypothesis is there is autocorrelation. Then the probability value is less than 5%. It means that there is a autocorrelation problem. Now go to the again quick same variable. The same variable, it is unemployment. Go to the that first difference. Go to the first difference, then click OK. Now you can see the probability value, the last column. So then you can see that in the second difference variable, there is no autocorrelation problem. Then you can see that there is an autocorrelation problem for the second difference variable. In the first difference variable, in the variable unemployment, the data series are non-stationary. It has that some graph. Select that only the unemployment. Right, this is you can't see there is some that reason in this is in Sri Lanka. So then after 2008 there is that is a sharp decline in unemployment. Right, again that again 2015 it is that it is increased. It increased. Then you cannot see the smooth pattern of the unemployment data series. That's why we consider the first difference of the unemployment data. Right, now let's go to the create that difference series. Generate D unemployment equal unemployment. Click OK. Right, then there is a new variable create, first difference of the unemployment. Quick graph, the same graph, unemployment, first difference values. Then click OK. Then the line and symbol. Now you can see there is that some up and downs. There is up and downs. These that shocks, unexpected changes remove from the first difference variables. That in the first difference variable there is no autocorrelation issue as well. So then the series are stationary. Right, same thing apply the same thing for the other variables as well. Apply the same thing for the other variables. Consider that it's a graph for the GDP. Right, draw the graph, basic line graph, line and symbols. Right, then this is the GDP data. Also now you want to check that parallelogram of the data series. It is GDP. It is levels. In the levels, it doesn't have that autocorrelation problem, right? It doesn't have no autocorrelation issue. If you want that, go to the parallelogram and then GDP is a plus difference, also no autocorrelation, right? It is okay. So then if you consider that for plus difference, for the levels, there is no autocorrelation issue, right? So then now go to the again another variable graph cancel. So then go to that another variable, go to the another variable, go to the pick graph, another variables capital adequacy CA, the line and symbol. Then this is the capital adequacy data series, right? If you can't that get the good idea about that is by using the weaving the graph, so then it is better to check the partial or correlation and autocorrelation and partial autocorrelation. Then go to the group statistics. It is parallelogram. Then variable is CA. Then click OK. First go to the levels. In the levels, there is no autocorrelation issue. That means the series are, because it is the ratio data, so then series are autocorrelation. Series has no autocorrelation. Then go to the another variable. Right, go to the another variable. One by one, each variable, the behavior of each variable, whether each variable has a unit root. So the first you need to go for the time series graph for each variable, and then look at the partial and autocorrelation and partial autocorrelation of each variables, and then need to think what order this process has, whether it is all are that levels, or whether all are the first difference, whether all are the second difference, like that. Right, so then do the same for all the variables in the model you are considering. Do the same for all the variables in which you are considering. Right, then that is next task is right, the next task is use the Dickey Fuller test. Or examine whether it is stationary or not. Right, what is the hypothesis? How to write down the hypothesis of the stationary or not? Our null hypothesis is the data need to be differenced to make it stationary. That is the null hypothesis. Then alternative hypothesis. Data is stationary. And no need to be difference. That for each variable separately check. There are that how many variables except that constant. All the variables, not that when you add new series, don't do that. For all the variables you consider, check the unit root. Right, go to the quick and the series statistics. Go to the here unit root test. Assume that that is unemployment. Right, first go to the level. Here that augmented decoupled test. In the test type, there are different type of test. Augmented decoupled test, and the other test is Philip current test as well. Levels, default, right, same thing. So then here first check the augmented decoupled test. Right, it is first go to the levels of the data series. Then in the first levels, it is augmented decoupled test value is greater than 5%. That means we reject our alternative hypothesis. The data is stationary and doesn't need to be difference. We reject it. That means our data to be difference to make it stationary. Then go to the second difference. Series is unemployment. Go to the first difference there. Go to the first difference. Then you can observe the probability value of the augmented decoupled test. It is less than 5%. Then we confirm that data no need to any more difference. Second difference variable, first difference variables are stationary. Right, then select another variable. All the variables in which you consider to the model. Go to the quick series unit root test. Then go to the GDP. Right, it is first levels. Go to the levels. In the levels, the data series are stationary because it is less than 5%. If it is less than 5%, means data no need to be data is stationary, no need to difference. That is the data series unemployment, right? Uh, then go to the another variable, series statistics. You need to test. Go to the CA, that adequacy AD, AQ, this variable AQ. So then click OK and the levels. Right, in this variable, first difference, levels variables are not stationary and they need to be difference. I need to consider the first difference of the variables. Then go to the that second first difference of the same variable. It is we consider that AQ, this variable. Go to the that select the second difference. The second difference, it is also non-stationary. Right, it is stationary, and it is stationary because that value is less than 5%. Then go to the next variable, series statistics. You need to test. Go to the CAR, that variable. First check the levels. In the levels, the variable CAR, right, that variable is need to be a difference, right? So then data are not stationary, so they need to be difference. Then again go to the quick and group statistics, series statistics. You need to test variable name CAR, click OK, and then go to the first difference there. In the first difference, you can see the probability value is 0.005. It means our data series no need to be difference again. That means first difference variables are stationary. Right, again that go to the next data variable. It is CI, click OK, and then go to the first levels. In the levels, these variables, in the levels, it is stationary. Then go to the again group series statistics, unit root. Go to the another variable, interest rate. Right, it is this variable also not need to be difference, but first the levels data are not stationary. Then they need to consider the second difference. Then go to the quick series statistics. Series statistics quick. Series statistics you need to test. It is data variable. It is I. Go to the that first difference. Then you can see this probability value. It is less than 5%. That means data series should be to make it stationary. Need to consider the first difference. Right. Likewise, you need to check all the variables whether they are stationary or not. Right. Ultimately, for data analysis, all data should be stationary at levels or all data should be, if it is levels, we use the word order of integration is I0. It is levels. Order of first difference we use order is I1. If it is the series, the second difference we use the order I equal second difference. That is the integration. It is integration is I equal 1. Almost all data are second difference is stationary. Right, now what we need to do is, if the data is stationary, then our task is to test whether if the variable are not stationary, assume that if the variables, that means your data series are not stationary, then convert the data to the first difference. Right. Right. So then after that converting data to the same order, then we can conduct unrestricted VAR model. So then in the here you can see that there is a quick, there is that estimate VAR. When we go to the estimate VAR, we can see that unrestricted VAR and the restricted VAR. This is vector error correction model. It is restricted VAR. Right, so then it is this model, and then we are discussing later. So then if the data series are stationary, first our task is, if you have a data series, time series data series, first check, don't that analyze the data series as it is, because it include unexpected changes. It include unexpected changes. Then what happened? Then shocks is usually used to describe an unexpected change in the variable or in the value of the error term at a particular time period. Then when we have a stationary system, effect of shock will die out. When we have a non-stationary system, so then if we consider the data as it is, effect of shock is permanent. But that effect of the shock, political election, that is a shock to the economy, that is shock to the share market, it is not the permanent, it is temporary. If you consider the data as it is, your data, it include these errors, these shocks. Then your shock, if you analyze, so then you analyze based on that shock. So then a shock is permanent. When we have in a stationary system, that's why we consider, we remove that change, unexpected change. Then the effect of shock, this unexpected change, will die out. Otherwise, so then what will happen? So then if we consider the non-stationary data, right, without that dying out the unexpected changes, right? For example, that if you consider the sales is high during the month of December and the January, but that's why we die out that unexpected change from the series. Otherwise, your results based on these uh, unexpected results based on these unexpected changes. That's why, so then here, very important when using the time series analysis, we need to remove these unexpected changes. We know that we are with the finance data, and the mostly that your research. Yesterday I saw most of your research based on the time series, right? I'm really wondering how that you are planning to analyze your data, right? It is that different. If you use the data and then analyze the data like by using normal regression, you can't analyze the time series data by using the normal regression. This is because it several shocks, right? It include shocks, right? Unexpected changes, right? If you consider 2009, so then most of the tourism sector, so then due to the world recession, there is a sharp decline in the tourism sector in 2009. That is the unexpected shock, right? So then in share market, the stock market or stock prices during the month of election, the period of elections, right? Government changes, so then it drastically impact for during only for that period. So then we need to remove, die out these unexpected shocks from your data series. Otherwise, if you do not consider these shocks or unexpected changes when using your time series data, so then what will happen? So then your analysis based on these shocks, then results are not realistic. That's why we call it spurious noise, nonsense regression, nonsense output. So then you can't use your model for prediction, for interpreting. That's why it is mandatory. If your data series are time series, we practice or that do the if you are not that following this lecture series, try to that analyze how to analyze your data set if your data set are time series. Right, so then what you need to do is, so then if you have that already data, if you have an already your own data set, so then first plot your data, right? Plot by using the plot your data, right? This do this task, right? Plot the data, and then looking at the graph, then you would expect your time series data are stationary or not. Then you can check the autocorrelation and partial autocorrelation of your data series. This is for what? To check whether there is an autocorrelation problem. Autocorrelation problem means past value impact to the present values. For example, in the consumption, right? When consider the consumption, our consumption depends on not this month income. In practice, our consumption depends on previous month income, right? If you analyze your data, your consumption depends on this month consumption, it is wrong. That's why if you do not consider, assume that consider that only this month income, so then do not consider the last month income, so then that is the error you do, then that error goes to the error term, right? It disturb for your regression output. That's what we are doing here. That's what we are doing. Right, then next week, so then let's discuss, so then practice if the same data set, or practice how to test the unit truth, right? What is the time series data, right? Why we are testing unit truths, right? There is a same same test here. Assume that GDP. There is another test here, PP test, first levels. Then you can see the GDP in the first level. It is same results what we obtained from the augmented Dickey-Fuller test, right? It is probability value is less than 5. The levels, it is okay, right? Go to the that another test. It is unemployment levels, right? It is non-stationary in the levels. Then go to the first difference. Here go to the first difference, series statistics, unit truth test, unemployment. Then go to the first difference and then check the probability value. If the probability value is less than 5%, then you can confirm that the data series are stationary at first difference under the PP test. So then do this activity, test the augmented Dickey in your that all the data series, check the plot the data first, then check whether data are suffer from autocorrelation or partial autocorrelation. Then check the unit truth by using augmented Dickey-Fuller test as well as the PP test. Right. So then upload that your homework, right, to the practice this and upload your work to the LMS. Right. If you have any that questions, please that upload, or the please that joined with the discussion forum. And then for the today, it is that what we have discussed, to check what is time series data, why we are that testing the time series data. It has that it has an unexpected changes. So then how to remove these unexpected changes by using the Dickey-Fuller and the PP test. If you have your own data set, and then please check all these and be practice. When that after that analyzing, after checking the unit roots, then our next task is whether there is a short run relationship of the variables and whether there is a long run relationship of the variables. That is cointegration analysis. So then next week let's discuss the cointegration analysis by using the same data set.